Mathematical modeling basics, and this is a little bit different, algebraic differential, and I thought I'll club differential algebraic also as part of this. So this has got a little bit of more fundamentals that you have done at your undergraduate and graduate level, but slowly I will build on to it. And today and tomorrow's lecture, I will try to give you an idea of how the solvers are built for the commercial solver, because these are the solvers that is running behind the scene in Aspen, AdSim, Aspen Custom Modeler, Aspen Plus, also MATLAB, Pyomo, and all those solvers. So I basically wanted to give you a glimpse of it, but I am not going into too much details into it. So feel free to ask me questions, or if you want more details, let me know. I can actually add on more materials tomorrow. So I'm pitching at a level that would be understandable more from how these things are implemented from that perspective. Okay. So first concept is dependent versus independent variables. So when we declare a model and we write some equations, the question is which variables depend on what? And you have done those degrees of freedom analysis, but sometimes this becomes confusing when you are using a software like Aspen where some models has been built. If you are the one writing the equations, you probably count it, like you'd say, okay, these are fixed variables, these are free variables, and count, and this I must fix it to make the degrees of freedom equal to 0, and that's how you go. But this is not obvious in a simulation environment, and over the years I have seen this is one of the biggest confusion that arises. And you will see that how Aspen treats it, what Aspen tells you, and what really happens. And those are the things we want to understand. So first is, really independent variables are the time and the space. These are the really true independent variable always. In addition to that, there are input variables, right? These are not necessarily to be confused with inlet. If that is not necessarily an inlet, we call it input or specified variables. These are also independent variables. The way to understand what is independent variables is something that does not depend on the model. It is you who can specify it. Like for example, some feed is coming into the system, it has got the compositions of so much of CO2 and nitrogen and oxygen. That is completely independent of the system because that is coming from somewhere else, right? Same way, when the feed is coming at your boundary and it comes at some temperature, temperature is an independent variable, right? Because the temperature, that does not really depend on the model itself. It's actually at the boundary, it's completely an independent variable. Now, I'll ask you a question. Is the flow through the system an independent variable or a dependent variable? Anybody, take a shot. So I have a flue gas coming through and going through an adsorber or anything, or membrane separator, and we're saying, okay, this is coming at the boundary and this is flowing through the system. Is the flow rate through the system, like meter cube per hour or mole per second or whatever, is that an independent variable or a dependent variable? Dependent variable. Because anybody who answered dependent, can you explain? Right, because I have a system there, it does not mean that I want to send so much of flow rate, it will go through the system. It really depends on the pressure drop of the system, what is my driving force in the system. So it is not. But the pressure at the boundary is an independent variable because that is coming out from somewhere. If I want to raise the pressure, I have to put a compressor or a blower or something, but the pressure at the boundary becomes an independent variable, that I'm saying it is coming at that pressure, but the flow rate is not. So you have to be careful in terms of what you specify. And tomorrow and day after, you will see that we will be actually discussing more with this. So when you look into a software like Aspen, you will see that it treats these variables as 3 different kind of variables, and I will be discussing more of those, and we'll be discussing these. One is free, another is fixed, another is initial, another is rate initial. So we understand that these independent variables are basically the fixed variables. That is what we are talking about. And then there are differential and algebraic variables which are dependent variables. Okay. Now you notice that here the thing to get a little bit confused here is the free, initial, rate initial. If you have a time derivative for any of these variables, there could be 2 different types. So if I have a variable dy dt, then this variable y can be declared as an initial variable or a rate initial variable, and we'll discuss what does that mean. But other than the differential variables, all other variables are treated as the free variables which you will be calculating. So when you write the equation, then you count all of your equations and number of variables and say, okay, now it is squared, or you say there is no degrees of freedom. This is a problem when you actually use a software like Aspen AddSim, because you drag and drop a block and you think it will work out. In Aspen Plus it does, because Aspen Plus does not let you specify any other variables than you can do. So for example, if you have 2 degrees of freedom, there are 2 blocks that you will expose to you. There is no way you can play with it, and or you can do anything with it to make it non-squared. But AddSim is not like that. Aspen AddSim will give you a lot of options there. So it's in some ways it's a free tool. So you have to understand what you are doing. So that's what we wanted to be clear here. Now there are 2 types of model. Again, we all know, and why I'm going into it, and that has to do with respect to the solver. And that's one of the big thing. And Aspen actually solve things very differently than many other solvers. So we'll talk about that. Those who have used MATLAB and who have used Python, there is a different way that Aspen actually treats this solution. So we'll talk about that. So first is the linear functions. We have, first thing is additivity. So that's important. So this is how it is given. And then we have the homogeneity, right? We understand these are the linear models. Anything else that does not satisfy these, like which are not linear, is called nonlinear, right? This is the best way to define it, because everything else is nonlinear that does not satisfy these. Now, what we see here is that most real world processes are nonlinear. Does that mean that we cannot come up with a linear approximation? Absolutely we can. In a neighborhood of an operating conditions, we can approximate many nonlinear models as a linear model, and they work pretty well, but within a defined conditions. And you have probably all studied that how to do it and around a neighborhood of some points. And generally one of the things we do is the Taylor series expansion, and then we can actually come up with a linear model for that one. But the reason I'm saying here is that based on the complexity of your model, you might like to make linear approximation. Many processes can be very nicely approximated as a linear model, makes no difference in terms of the results, but your complexity actually goes way down. So my suggestions always, like even with all the advancement, is that if you can make a linear approximation, make a linear approximation. Okay. But in this case, you will see that there are some high nonlinearity where if you make a linear approximation, there will be a lot of error. So in that case, obviously, we cannot do that. There is also the other questions is the lumped parameter and the distributed parameter model, right? When you do the lumped parameter model, the only independent variable is time. We're basically saying I am ignoring the variation with respect to space. Okay. When you think about an adsorption process, and we'll be going deeper into it later on, but when we think about an adsorption process, there are a lot of changes happening with respect to the space. But if we are saying, yeah, I do not, there is a process where there is not much change happening with respect to the space, I can always use it as a lumped parameter model, right? What is the advantage? It will, if you just approximate this as a independent of the space, it becomes an ODE, right? So what we really do is, in some sense, that everything has been, dependency of all variables have been lumped into the form of a single variable, we are saying, with time. So nothing changes with respect to the space. Like we always say, CSTR is a good example. And we always get confused, like when we read in the CSTR and you go to and walk into an industry and you keep thinking about which reactor in this process is a CSTR. Right? It's confusing, and in the book the first chapter we start with reaction engineering, say, oh, this is a CSTR. Which one is a CSTR, right? You always keep thinking about it in real life, right? But the idea is that there are many processes which can be approximated as a CSTR. And that makes you very simple way of thinking about it. Can anybody think about a very common application which can be very well approximated as a CSTR, or a lumped parameter model will work pretty good for those type of things? Any example? Like in real life, we always use, we use at home, we use everywhere actually. Also industry, anybody? Generally ignition or the combustion processes. Many combustion processes, because it is actually instantaneous, and if you are really as a well mixed systems, it will be almost instantaneous. After that, the temperature can vary, but the compositions, it comes there, it will combust, it will immediately produce CO2, like our cooking, right? You are combusting the natural gas, like you are burning the gas, and immediately after this it is CO2, mostly CO2, and there is not any change with respect to the space. After that, you can just consider a heat transfer problem. So front part of it can be approximated as a CSTR. After that, you can simply do solve a heat transfer problem after that. So this is the way of practical modeling. But in here also, I will be talking about some types of adsorbent beds, not the fixed beds, but some types of beds can actually be approximated as a CSTR. Those are like things like a bubbling fluidized bed, right? That's another technology for adsorber that can be considered as a lumped parameter system. Any question so far? Clarification? Okay. Now, if you go by the lumped parameter system, the order is given by the order of the ODE, right? So if I am saying that it has got an nth order system, this will be described by nth order ODE or by n first order ODE. This part is, we study this, but I have found it to be many times confusing, because sometimes we actually use a second order or a third order ODE here, but that may be because I'm lumping different mechanisms together. So in first order, but I just lumped it, and I'm just observing it as a nth order system. That's the way we do model it, but mathematically it makes sense that if you can actually replace that as in first order ODE. In Aspen, this gives you all the opportunities, but there are pluses and minuses, and that are the things that which we'll be talking about. That it's not straightforward, like we say that, okay, if I have an nth order system, I have a second order system, and I can approximate that within first order ODE. It's not mathematically, they are not equivalent. They will be, numerically they are not equivalent. They are mathematically equivalent, but they are not numerically equivalent. So those are the things that we need to keep in mind actually. Now this distributed parameter model, the process variables will vary with spatial location, right, as well as time. And so what happens is, like, when you think about an adsorption bed, and we'll be discussing more with this, something comes in and that adsorption front actually keeps moving forward, right? So the front actually keeps going forward through the system. So this is actually a distributed system. This makes it very confusing when you try to use it for optimization, because it is inherently a dynamic model. I'm not sure how many of you work on dynamic optimization. Do any of you work on dynamic optimization? Okay, so as you know, that dynamic optimization is actually complicated and difficult and involved. But if I give you an adsorber model and I say, yep, optimize this system, you are solving a dynamic problem. There is no way you can solve a steady state optimization like you open up Aspen Plus and optimize it. Cannot do it actually. So this makes it complicated because of the distributed nature of the thing. So I'm not sure, I missed Dr. Datta's presentation, but I think a little discussion about the adsorption bed is in order so that you connect dots why I'm talking about this. So this is kind of an adsorption bed, so the feed goes there, and this is actually, so CO2 rich feed, and we say CO2 lean product, right? This goes out. So this is how it goes through the system. So this is a front that moves to the system. So what happens is, each location, the loading changes with respect to the time, and then this all the variables changes with respect to the space. So for adsorption system, this is inherently dynamic system. There is no steady state for an adsorption. It cannot be approximated as a steady state system. So it goes under the distributed parameter model. Okay. Any questions so far? Okay. Now, other thing is continuous and a discrete time model, right? When we mostly will be discussing about the continuous time model, like this type of equations. We say dy dt equal to f of y x theta t. So this is the type of a model. The problem comes there is that when you go to an experimental system and somebody measure one of the variables like these outputs, they will give you it as a time series data. So if somebody is observing the composition here, so it will say product composition, right? And this is with respect to time. So we'll say T0, T1, T2, T3. They'll give you Y CO2, Y nitrogen, Y H2O, and all of those, right? So you will get all of these data. So this is our observation. Even though it's a continuous, actual process is continuous, our observation is discrete, right? So that is what we'll talk about this. So it becomes confusing actually that how can you actually represent this discrete time data with respect to continuous time? Because, and this is the reason why you have to be very careful about here, is that Aspen will not necessarily give you a particular solution at those points, not necessarily. So this is the problem. So when you are solving y with respect to t, say Aspen gives you a solution like that. This is what we call a breakthrough curve. Your data points are basically here, here, here. So what you can do is after you solve the problem, you can just plot it and say, oh, my model is not working well or working well, whatever. But if I ask you that take these 3 points into considerations in this particular time and solve an optimization problem to obtain the parameter of a, say, mass transfer coefficient parameter, then I'm talking about getting a solution at these exact points there. How do I incorporate that in the solutions? Because Aspen is solving continuous time, your observation is discrete time. So how do you connect both the dots? So that understanding is actually important for you. You can actually plot it and say, oh, my model did not work, but can I improve it by taking that into consideration? It's almost like you do trial and error, but is there could be systematic way that these discrete points can be taken into consideration and for estimating or optimal estimation of parameters. So that's why it is important for us to understand this. Yeah, so the issue is that in a computer controlled systems, often what we get is sampling of the variables are at discrete point of time. Does this overall approach has got any method, any merit in it actually? So we always say that this is a continuous time and Aspen is solving it in continuous time, or any solver like MATLAB is solving or PyMO is solving at continuous time. Is MATLAB or Aspen or any other software, can it solve it continuous time? Does it solve continuous time? Anybody? It does not, right? It has got discrete interval at which it is solving it. So it does solve it, but how do you tell the software you solve at this particular point? Because I'm interested in those particular points, right? So actually the thing is the real physical system is continuous unless you get an analytical solution which is not practical. It is always, even with those software, it is discrete. It is that it actually connects these lines depending upon whatever software you are talking about. It makes it either like a cubic interpolations or a locally linear model. That's why it actually looks up like that. It seems to you that it is continuous, but it is not. Behind the scene, it does not have the information. So just to ensure, when you look at a plot, do not assume that it is doing something continuous. It is not. So real life is continuous. Our observation through a computer control system is discrete time, and our solvers are also discrete, doing discrete calculations. Okay? Okay. So how do we set up this type of a model? Like first is this input output type of a model, this one. These ones are the most simplistic. Basically I am saying I don't want to understand anything that is happening. You give me the input and output and I'll give you some of the, give you a predictions. Like for example, a lot of machine learning models are like that, right? We are basically saying, you just give me the data, I will fit it. I don't want to understand what is going on. I'll give you a functional relationship between input and output. We use these type of models for process control, as you have all studied quite often, and now a lot of artificial intelligence, machine learning, data-driven models are all in this domain that which we are considering. But we are not interested as part of this class on this side. We are interested in these models. So essentially what we wanted to do is a state space model. We write it as a continuous time, that's what I highlighted it here, and then this will be all distributed parameter and nonlinear. So this is the class of the problem that which we are trying to solve. So remember that I talked here about the continuous time. That is because how we write the equation. The problem, the solution technique is different, but this is what exactly what we will be solving or writing the equation as part of our work. Anything, any clarification? Okay. Now, I already said that we have got the order of the system is actually very important. So first order means that we have one differential equation, second order we have got two first order, and third order, and so on and so forth. So what we do there is that first thing, and the simplest one that you have studied mainly in your controls class and solved it, and this is something you can actually solve it very easily in a software, like if you are using one of the ODE solver like ODE 45 or 15s or anything like that in MATLAB, you will be able to solve this problem easily. Now, what are the things that we are actually talking about here? So let's be clear from an adsorption process what each of these variables mean. So this X could be all these composition variables over here. That is, if I say, when I say composition variable, composition of what? Composition of which type of species? Is it gaseous? What else? Also the solids, right? Because the solid loading is changing, because we need to compute that. This is the difference compared to other processes, because I'm actually changing the loading as the gas, as the molecules are moving from the gas phase to the solid phase. So the solid compositions are also changing. But there is a catch here. Only the gas flows through the system, solid is stagnant. Solid is just staying here, right? So we'll be discussing that how do we model those, but that's what we are actually doing here. So this could be all the compositions, and then we have these U, which could be your other things, like for example your compositions, the flow or the pressure or temperature or anything. And then these disturbance variables could be something which you cannot control. For this work, which is just focused on the simulation, we do not really distinguish between this type of variables and this type of variables. For us, everything is something that is, we fix it, right? And the other things we are calculating it, okay? Now, what is the one of the first type? The linear lumped parameter continuous time. I'm now actually keep moving here, is that like go to the second order state space model. There are two equations, and it immediately becomes more complicated. And when you look into this, so what is the issue here that is coming, and I'll talk about that in a moment here, that you have these two variables. Now, if I'm actually considering it with respect to the space, and I'm trying to come up with the compositions at each of these locations, and I find out what is the thing that I'm trying to come up with it, so we have to write many equations, and then these only time derivatives are not sufficient, because this is a lumped parameter system that I'm writing here, right? So this is not appropriate for writing an adsorber, but this is a simplistic model that I think practically all of you have solved as part of your undergraduate class and part of the graduate class. So we know how to solve all of these, right? So so we just write it like this, and this gives you a state space form. I wanted to show you this one because this is our favorite equations we always used in the controls class, and I was very happy about it. And they say, okay, this is a standard state space model, and I control it. So we'll actually divert from here to say that, okay, when this is the picture we have gotten. Now, yeah, so this is the picture we have gotten. Now we go to the actual process model and see how the real process model differs from that simple description that we had. First, think about how we write a process model. We write simple thing: accumulation is equal to in plus some generation minus out minus loss, right? That's the standard way of writing that one. So if I'm writing this for the mass, we said accumulation of the mass is whatever is from the in minus out, right? And then species conservations, we say, well, whatever is the generation of species A and outlet rate of species A at outlet minus rate of consumptions of the species A and all those stuff. And then we write the conservation of energy in the same way, right? That energy in, out, and generation and loss, all of those things here, right? We can also write momentum conservation equations or the pressure drop model, right? Those things as part of this. But one of the things that what you really need to think about it in general in a simple classroom type of a project, we don't write that, is other constitutive equations. First thing is the physical properties. This is where the strength of a software like Aspen comes in. Otherwise, you can use MATLAB or Python or anything for this. The first thing is this physical properties. So physical properties, for example, if I do the viscosity model, thermal conductivity, diffusivity, surface tension, these are our transport. So how a molecule is getting transported inside the adsorbent, how the CO2 enters the locations where it is going to be adsorbed. So some of the CO2 getting adsorbed, some actually flow through the system. How should I describe it? What mechanism by which it goes, right? So in general, if we think about the transport mechanism of molecules, what are the typical transport mechanisms of molecules? Can anybody tell me? Generally, how do we model it? What are the transport mechanisms for molecules within a solid? So if I think considering a gaseous molecule, and the gaseous molecule is getting inside the solid, by what mechanism would it go inside the solid? Diffusion, yes. What else? Sorry? I heard capillary, okay. What else? Yeah, that's how the water gets into a lot of the rock structures also. What else? Actually, it can be very complicated. It really depends on what that molecule does with respect to the solid and how it interacts with respect to the solid. If you think that the transport essentially takes place only in the form of molecule, then diffusion and the diffusion induced convection, local convection, is the real mechanism by which it will flow. But depending on what our other species gets formed, the mechanism can actually greatly vary. Like many times it can actually form some kind of a charged species, and it can actually jump from one location to the another locations. So internally, how the overall energy works out and overall transport mechanism works out, that depends upon in what form the molecules get transported. Is it essentially only molecular transport, or it is going through some other spaces? We'll be also discussing some of this kinetics here in more detail, so I do not want to spend more time here. But the point here is these physical properties model, what type of equations do we write for these? These are differential models, these are algebraic models, or what it is? Let's focus on these one first. The transport properties model. So what type of model equations are these? We heard differential. We heard something else. Go ahead, don't feel shy. Yeah, but if we just simply go by the property, right? Like for example, if I say go by the diffusion coefficient, then we write an algebraic model for diffusion coefficient. But when we describe the mechanism, that how the diffusion takes place, it's a differential equation, right? Similarly, when I'm looking into the thermal conductivity, that model is an algebraic model. But when I'm saying how the thermal conduction takes place, right? If I say that okay, we are using Fourier heat conduction law, then becomes a differential equation, right? So it can be both ways. So these properties, which is basically all the model that Aspen will be pulling for you for the species that we are interested, it will pull lot of these algebraic models. So when I say these are all becomes your algebraic model if you are just focusing only on the properties. This is one of the big things that which we need to discuss, the thermodynamic property model. Now, what is the parallel of a absorption with respect to adsorption? In absorption, AB, absorption, that is liquid gas, right? The equilibrium is between vapor and liquid. In adsorption, the equilibrium is between the solid and the gas, right? So in adsorption, we have already know, okay, vapor liquid model, how do I represent the vapor liquid model? We have a activity coefficient model, like there are only two models that which we use, right, for vapor liquid equilibrium. Either it follows Raoult's law or it follows Henry's law. And then using the Raoult's or the Henry's law, we then write in form of an equation of state, or if it is some liquid that does not follow the ideality, we use an activity coefficient model, and that's how we actually go for it. But adsorption, you just had the class before, so we write the isotherm model. So it's a completely different way of thinking about it. It's instead of that equation of state, we actually write a isotherm model, but that's an equilibrium model there, right? So, however, I still write equation of state under the thermodynamic model, and you can come to me and say, what are you talking about? This is not in a gas solid system. We are not talking about an equilibrium in terms of equation of state. This is only for absorption. So why are you using, why we need an equation of state here? Anybody? Do we need an equation of state in an adsorption model? Take a shot at it. It's a thermodynamics. We'll go all over the place, right? We'll go to the math, we'll go to thermodynamics, mass transfer, heat transfer, fluids, everything actually. So let's think about thermodynamics. So equation of state. Do we need equation of state? Where? Why? Right, for the molar density we need that. What else? Gas properties, like which properties? Yeah, pressure temperature changes, and so the density is one of the things that is we need. Another thing which is equation of state is absolutely critical for that. Temperature. So what is the equation of state used for? Say that. Be loud. Be loud, please. What do we calculate by equation of state for gas properties? You are right, for the energy we need that. But what is the thing? We use it for excess enthalpy calculation, remember? Like the delta H excess, like we have got, when we write the enthalpy model, we write it as an ideal gas, plus we have the non-ideality. How do we calculate the non-ideality? This is all gives by the equation of state. So if you are using SRK or the Peng-Robinson or any other equation of state, that's the guy that is used for calculating the delta H excess. So we are not saying unless I say this is an ideal gas. If I say it's an ideal gas, I do not need an equation of state. But if we say this is a real gas, right? So we will need this equation of state here, right? The same way we might be needing the vapor pressure, and if we do not have the liquid here, so anything related to liquid, we can actually ignore this. But this is a general list of it that which we are considering here. Now I said here chemical and the phase equilibrium. So chemical equilibrium, do we need it here for anything? For a typical adsorption, right? Let's brainstorm. Do we need chemical equilibrium for considering anything? If we have a chemisorption, right? If we have a chemisorption, we might need to describe the chemical equilibrium. So an isotherm model is an approximation. Sometimes it is confusing. You say, oh, my system is undergoing chemisorption. I could fit this isotherm model. What are you talking about? Where is the chemical equilibrium coming into picture? That is, as I said, that's not a true representation. It's kind of a isotherm model. You have to kind of think about a data-driven representation of it. It does not necessarily tell you anything about the mechanism that is going behind the scene. That the same solution you can get from a more mechanistic model. And if time permits, I will actually show you the parallel. Actually, one comes from the very fundamental level, and another is, I will just simply show you an isotherm model that will fit to the data. Perfect fit. But that does not tell you about anything that is going behind the scene. So all those things are possible because the chemisorption is very complicated. Very complicated. The fact that you could fit an isotherm model does not mean that you understood really what is going behind the scene. So it will work fine in mathematically, but in terms of mechanism, it might not say this. So we may need chemical equilibrium there. So what happens is that one and also the kinetic rate equation, like when we use an Arrhenius type of rate equation, right? Like we said, reaction rate is equal to A exponential minus E over RT, that type of formulation there. All of these are my algebraic models. So just to ensure we are on the same page, these conservation equations, these are all given by differential equation. Remember at the end of Burt, Stewart, Lightfoot and all your transport class, right? All of you taken that all these equations that you have done in your transport class, those are all differential equations. Those all goes here, right? But at the top of it, there are other equations that which we need, so which are all these equations, and that is what goes into the picture. The reason I am actually getting into a nitty-gritty of it, because when you actually do Aspen AdSim, behind the scene it will actually keep pulling lot of models here. You will not realize what it is pulling, right? So you have to understand it. The problem is, do you need to understand? Yeah, absolutely we need to understand. We are all researchers. We need to understand what it is pulling behind the scene, because otherwise when it will fail, or the results, I cannot interpret the results, or I cannot modify, right? That's why we need to do this. And then there could be other equations specific to a particular system that we need to describe that particular system, okay? This one, okay, I'll leave it. So yeah, some font here probably is not right, but you can understand it. So this is an example problem which I will be working tomorrow as part of our workshop. So I thought I will actually describe it today, and then tomorrow we are ready for our workshop, and we'll be modeling this, and you will see that how these equations it brings, and in Aspen how you actually model these things, because AdSim is built on this framework. That software on which it is built is Aspen Custom Modeler. So we'll be discussing that here actually. So let's think about it. This is a reaction that is taking place between methanol and acetic acid, and this is the reaction. Let's, for simplicity, we'll consider isothermal systems for this one. So if I consider a species conservation equation, I can simply write it, and this is for a CSTR, F in and this is out, and then this is plus minus reaction rate. It depends upon which one we are writing, which species we are writing, what is J, whether this guy, this guy, this guy, or this guy, depending on the sign will change plus or minus. If I am writing setting the derivative equal to 0, this is a steady state, this becomes an algebraic equation model. So this becomes only this. So remember what I said, it's the species conservation, it is really the conservation equations that gives you the differential model. There could be other differential equation. I'm not saying there cannot be other differential equation, but mostly the source of the differential equations for process model are the conservation equations, but then there are others as well. But this is the species conservation, and for a CSTR, if I set this to 0, like for steady state, then I do not have any differential equation, because all other properties model and everything, these are all algebraic equation. So the overall equation, system of equation is algebraic here. If I write this one, it will lead to, this is a differential equation, and then other models like the properties models and others are algebraic, so it becomes a DAE model. And we'll talk about this tomorrow, how to solve this guy, but today I'll be focusing on something else. Now, what are the other equations that we need to consider? One is the summation of the mole fraction we'll be considering. Then we'll relate the concentration to the density, okay, and then we'll have the specifications for all the properties, right? So we'll write these equations tomorrow in Aspen Custom Modeler, and I will show you really how to solve it. So what I wanted to show here is, one thing I wanted to tell you here is that there is a fundamental difference between how you solve these algebraic equations like in a solver like MATLAB versus Aspen. And so keep these things in your mind. If you have never used Aspen Custom Modeler, like which is where the AdSim is built on, Aspen Custom Modeler, the solver solves everything together. MATLAB doesn't do that. In MATLAB, you have to call a routine like fsolve. You say solve this system of equation. But for Aspen, the solver comes at the top of it. So it basically grabs everything and solve it. So you don't need to worry about it. You don't need to say solve this one, this is my initial guess, this is this one. You don't need to tell anything. It will automatically grab everything and solve it at one shot. So that's a fundamental difference between those. So what you will see, we'll just simply write all of these equations that what we are talking about. It's part of. Now, in this case, out of this total discussion, what is the properties model that I need to write here? So I will go over this equation again. So remember what I said, I have to write a species conservation equation. This is what we wrote here. And I write Rj, this equation we can write, okay. So look into these two equations. If I write this one, and then I assume that you are substituting this equation here. And then we are writing this mole fraction, and then we are connecting this to this, right? What properties model do I need to consider here? Properties model for what? Do I need any properties model? Let's think about it here for this simple problem. Like I was always saying, yeah, we must use equation of state and all that kind of thing. And I give you this example, and you can come to me and say, yeah, why are you using properties model here? Tell me, are we using properties model here? Do we need equation of state? Yeah, do I need to specify anything, or it will go forward? This guy, remember we talked about this, the density? Yeah, that's why we need to have this, because how do I know what is the density of this material, right? So we have to have a properties model, right? Now, then, so the plug flow reactor, the CSTR was an algebraic equation. Now we expand it and we say, okay, let's go to the plug flow reactor. And here we write this equation, the standard equation here. And again, you are familiar with these equations. There are many different ways this is written in terms of V and X and Y, and this goes on the other side. You are familiar with this. But this is immediately it becomes a differential algebraic equation. So I need to now think about how do I solve this combined system of differential and algebraic equation. Then obviously the other equations are similar to the CSTR model. The moment it comes here, it brings a new complexity. I said here you need a boundary condition. So for this equation, can anybody tell me why we need boundary? How many? and what conditions are appropriate. Okay, so how many sorry, how many boundary conditions do we need? Somebody said something. And don't be afraid, just say everything is right. No, this is a workshop, we're working together. Say anything you like, nothing is wrong. One, right, it's a first order differential equation, we just need one boundary condition, right? What should be the boundary condition? Sorry? So just like we did a plug flow reactor, right? So this is a plug flow reactor, typical one. And we are saying something is coming in and this is going out, right? This is a PFR. So in these equations, what boundary should I provide? CI we provide, right? So we have got, like I said, 4 species. So we provide for all 4 species, right? You see we have, yeah, we have got 4 species here, right? So do it for 4 species. So I say I is equal to 1 to 4, right? And then what else? Do I need to provide still anything else? Yeah, also U, right? Because if I wrote it everything inside here, right? And if you are saying that you can change, again, you can consider this to be constant and not changing. That's okay. But if you have that, otherwise you have to provide the U values also at the inlet, right? So those are the thing which we provide. The boundary condition, this is an important thing, and when we look into the Aspen adsorption model, we'll be talking about this. A lot of these things are actually difficult for the desorption part. What I have realized is adsorption is generally can be straightforward and easy to understand, but the desorption can be tricky actually to understand it. So we'll talk about that. And then we have the additional equation as the CSTR model, right? Now, now we wrote 2 types of models. One we wrote algebraic equations, another we say differential algebraic equation. Now how do we solve these models? This is the next part of it, right? This is the most important part, right? You cannot come up really with an analytical solutions. I know we as part of our graduate class you have solved, like for the transport class, when you have solved the PDE problems, right? Combination of variables or separations of variables, those all these methods, you have solved only one equation there. Now if I give you 10,000 equation or I give you 1 million equation, can you solve it actually? There is no way you can solve it analytically, any of these. So you have to solve it numerically. So question is, how do you solve? And most practical chemical engineering systems are numerical approach is the only approach, right? You can come up with only numerical approach. Now, the standard approach is that, remember we have the spatial derivative like this one, this derivative with respect to the space, right? This derivative, the standard approach is that this derivative is discretized using one of the finite difference schemes. So when you will use Aspen, you will see that it will give you the opportunity to call one of such finite difference schemes. So let's see what are those and how they work, right? So if I have a first order derivative, sorry, this one a little down, so you can, hopefully you can read this. This is a first order derivative. So the simple one is the forward difference method, right? So f of x plus h minus f of x. This is the backward difference, and then we have the central difference. These are the 3 approaches that which we can use for this. So where should I use these to look similar? So where should I use forward difference versus backward difference? So for example, this case, this one, should I use the forward difference or the backward difference? Looks equivalent, right? Sorry? And the because? Right, let's look into it numerically what happens, right? So if I start at this location, right, I'm marching onwards, right? So it is saying that if I'm actually solving it, say I'm discretizing it like 0, 1, 2, 3, like that. So this space is being considered is bunch of discretization. So if I'm applying this equation, and I'm saying if I do it at 0, right, we are saying f of, at this point we are saying f of x plus whatever it is, right, h, meaning this will be at the 1th location minus f of 0. So that basically means f of 1th location minus f of 0's location with h. So it works out fine. There I have no issue here. So what I do here is, this is, I just provide the boundary condition here. So this becomes my boundary there. So if I'm doing it with respect to concentration, so this is my inlet concentration, or this I gives it in terms of the velocity, concentration, temperature, or whatever. So I'll just specify it and it will be fine. But what happens if I try to use a backward difference with the same scheme, that if I'm actually trying to do it here, you say if I do it f minus 0, then it will say f0 minus 1. So it's kind of pushing on this side. So it doesn't work out that way. So that I will apply when I'm actually looking into this side of the boundary. So really, the cases where this flows comes, one flow goes this way, another flow comes this way, I will probably use a forward difference this way or put a backward difference this way. Or I have to rotate the axis. I can shift everything one forward to apply those. Why this is important here is that adsorption processes, and we'll discuss that later. I just wanted to use, these are the outlets, so this one coming here. Adsorption and desorption actually switches side. So this, from the side the adsorption gases goes, ideally the desorption system, the desorbing gas will enter from the other side. So if you are doing the discretization yourself, it does not matter which is your 0 and which is 1. I can just simply rotate it and say this is my forward, but you will have apply one side forward, another side will apply backward to be compatible with this. They are similar and their order is similar, but it really depends upon where you are setting your axis and where is your boundary. Now, is this understood? Anybody needs any clarity? Okay. Central difference, yeah, it has got better accuracy. So why don't we use central difference all the time? You will see people actually hate using it. I already gave you the hints that there is some issue here. What is the issue in using a central difference? Right, because you have to kind of see this is a really gives you a plug flow, right? F1 depends only on F0, F2 depends on F1, and so it will be actually marching like a plug flow. When you look into this, so if you look into that one, if I'm applying it here, so this one, say if I'm considering F2, right, it is not only it is F0, it is going to F0. Then when I'm doing F3, it will become F1. So this crisscross way it compels that the whole thing needs to be solved together. What is the problem with that? When it comes from a solver perspective, when you actually do the matrix decompositions, and I'll be talking about that a little bit later, from a linear algebra perspective, this thing will come like a banded structure. It will be coming like this actually. So it is easy for you to solve it like this, because I can independently solve this guy irrespective of what is happening here. So it will be actually a banded structure that at which will show up. It's easy for the linear algebra perspective, but the moment you do this, this will make your solution much more complicated. So as you know that in the fluid dynamics, like if you any of work with the CFD, this leads to an oscillating flow actually, and be very careful to stabilize it. So the solutions can be very oscillating for when you try to apply this. But nevertheless, you can do it. Now, the second order derivatives also the same way. So you can do second order forward difference, second order backward difference, and the central difference. And then these ones appears in case of, like you will see, okay, that probably cut, but I'll tell you this. When you are doing the Fickian diffusion, this actually appears for the transport within the molecular species transport within the solid. So in that case, that's a second order differential equation, and then you will, when you try to apply the discretization, so Aspen does it behind the scene for you, but it actually applies one of these methods based on what is specified, because there are second order equations, and we'll be describing those as part of ADSIM, what it does and all of those. But these are the second order derivatives because we will be considering Fickian diffusion within the molecules and based on whatever mechanism we consider. The other one, the same things, the energy conservation, Fourier law also does that, and the dispersion also requires you to consider a second order model, right? Remember the dispersion equations is given by some k terms d2c dx2, right? So this is a second order equations, again can make your life miserable in terms of solution, but this is also used for second order. But so once you approximate these derivatives as in form of a algebraic equivalent, it converts everything to an algebraic equivalent. Just want to ensure we are all on the same page. So the technique is that when you have these differential equations with respect to space, you apply one of these forward or backward or the central difference. These are all finite difference schemes. The moment you use the finite difference schemes, these derivatives are replaced with these algebraic equations. That means that now you will be solving only algebraic equations. Is this clear to all? Because I'll be going forward there with. So in Aspen, when you solve it, the only thing you would like to solve is the time derivative. Is it not possible to use a integrator here and as well as for the time? Yes, you can. It just makes it very, very difficult because there is an inner nesting loop that has to work out. But in Aspen, that's not how it is actually done. So I'll talk about that more. So all the spatial derivatives are discretized to convert those derivatives to algebraic models, and so that already properties model are algebraic. We are converting these to algebraic. So I will only solve algebraic equations. Okay, so now how we solve this? So first is, again, I'm sure in your numerical methods class you have done a lot of those, but I would like to say a couple of things here that we have to be considering as we move forward. So first is, when you solve the system of equation, everything is actually of this form, right? So f of x k equal to 0, I want to solve it. So this is the approach by all the implementation that you will see. These are all derivative based approaches, right? So in Aspen internally, they do not use any derivative free approaches. There are some newer generations approaches that are showing up, but all approaches that you will see as part of ACM and ADSIM, these are all derivative based approaches. So they all are variants of Newton's methods. So different flavors of Newton's methods, but they are all derivative based approaches. So how they work? So this is the derivative. So xk plus 1 is equal to xk plus alpha k pk, and then we say gradient of f of xk pk is equal to minus f of xk, right? Now, don't get confused here that these are all greatest solver, but we can only find the local minima here. So if you have a multiple minima, you have to use some of the global solvers, and we can talk about that more. But with these solvers, it will only find the local minima, just like as you will see others. These are in linear equations. You can clearly see that if I have got so many of these, so I will have, this will be the size, this will be n by n, and I will be solving for all of those there. So ultimately what you are seeing here is, we started with a differential equation, then we converted that to algebraic equation, we said those are nonlinear, but then finally we are solving a linear equation. So the guy who brings all the capability of a solver is linear algebra. All the strongest linear algebra solvers, and it's still very old. All linear algebra solvers are still very old, or everything in MATLAB, in Aspen, still very, very old. There is no modifications there, because all the greatest development that has happened in linear algebra, those are all there. So behind the scene, at the end of the day, I need to solve the linear equation. So remember here, even for Aspen AdSim, doesn't matter whether you are solving an integration problem, nonlinear equations. At the end of the day, you are actually solving the linear equation. So when you will see in solver in Aspen Custom Modeler, it has got bunch of settings for the linear algebra solver. It has got bunch of settings for nonlinear equations, but that is completely different thing. So when we go there, we'll describe that. But let's see that why we cared about the linear equation solver. One thing is that we need first derivative. I'm not sure how many of you have heard about AD, or automatic differentiation. Okay, so so if especially if you're interested, read this. I'll not get into that more here, but Aspen does not still employ that, but this is known as automatic differentiation. This is an approach by which you can calculate the derivatives. Aspen still considers derivatives to be numerical derivative calculation. So these derivatives, all the Jacobian calculations are still considered to be only numerical based. So what it basically means is that if I am actually it basically comes from the fundamental properties of anything, right? So if I'm trying to calculate this derivative, I'm simply saying f of x plus delta x minus f of x, right? And then I'm doing the delta x. Technically this is delta x tends to 0, but this is the overall approach. And then you have gotten these small steps that you take, and then they try to calculate it numerically for any of these things. And this is actually the root of all problems. So these approaches are very good, but this derivative is a local approximation. So because these derivatives are not accurate, based on that you cannot make a determination how far you will go. So that is why this alpha k is less than 1 most of the cases. If we can make alpha k equal to 1, this is known as the full Newton step. If you can do full Newton step for any of these, wonderful. Only couple of steps you will see you are getting the solution. But most cases it will keep cutting step, cutting step, cutting step, and so that's the problem. So question is, I'll talk about a couple of those things here. So this method can fail. Now when we actually teach you Aspen AdSim, and you will see that it starts failing sometime or quite often. Even ACM when you actually see that you cannot actually solve it. And the general thing that which we always think of, say, yeah, the solver is not good, right? But this is really the tussle between the solver developers and the coder like us. I will write the equations and I hope that solvers solve. Fact is, there is no solver in the world that can solve any problem. You have to be careful as an user. So you have to help the solver to solve your problem. So if the problem doesn't solve, look into your equations. So that is why we need to understand why it fails, right? First is, this method can fail even if the solution or the roots exist. Many times you change something and it comes up with the solution, and I say, okay, this is crap because I just did not do anything and it solved already. So why, right? So first is, one is the poor initial guess, like where you are starting. So you have to remember from a numerical methods class that the initial guess is an important step. The reason is because I'm starting, where I am going, it depends upon where I started, right? So this is important, where I started. The other thing is that the first derivative can be ill-behaved in the neighborhood of the roots. So when you are approaching the solutions, it can become ill-behaved. Like, what does it mean, the ill-behaved? Like, it may not be differentiable in the neighborhood of the roots. Maybe the derivative becomes 0 around the roots, and the linear system of equations can be ill-conditioned. So when it is actually trying to decompose and solve the problem, it cannot, in essence, it does not invert it, but when it is in some sense, you cannot, if this matrix is not invertible, then it becomes actually ill-conditioned. So as you are going to the roots of it, maybe it is not getting invertible anymore. So that's one of the problem here. So does anybody know from your linear algebra class how such linear equations are solved? This is a matrix, right? And how is equations like these are solved? So remember, this is a standard Ax equal to b. That's what I wrote. So this is like this, equal to, so this is a vector, this is a vector, and this is the n by n matrix, right? How do we solve this type of equation? X equal to b, right? Go ahead, very good. Sorry? Okay. Anybody else? Sorry? Yeah, so most cases what we try to do is actually, the standard technique is to do a decomposition, okay? Very standard approach is actually do a decomposition. The most standard way to doing it is either doing an LU decomposition or an LDU decompositions, right? So in that case, if I'm simply doing an LU decomposition, this will be like, we put it in form of a matrix. These are all zeros, and this is the other way around, and this is all zeros, right? So this is the upper diagonal matrix, this is the lower diagonal matrix, and we do the decomposition, and that is how we solve this. You can also do an LDU decompositions, you can do the QR factorizations, I'm sure that is what we are talking about, and that is how you do that. But this LU itself, like for example, if you look into this LU decompositions, I said these are, when you actually decompose it, right, if what happens is that if anything, so like for example, if this component becomes 0, like anything on this diagonal becomes actually 0, then you are in trouble. And so when you try to get one, the L11, L12, L21, L22, all of these things here, and you are in the diagonal, it becomes 0, then you are in trouble, actually, because you cannot determine it. So because this becomes, everything becomes 0, there is no way I can determine anything about it. So, so that's the trouble that the solver is running into. And that is why it basically say I cannot do anything about it. So that is one thing what you have to do it. We are expecting a quadratic convergence rate, like as we know from the Newton's methods, right? We need another thing, even though we are not calculating the Hessian here, this is which you know, remember for and optimization, so we do it here. But even for these systems, you can only get the quadratic convergence rate if the Hessian, so the second derivative here, is actually continuous in the neighborhood of the roots. And if it is not, then you will not get that. You will only get a linear convergence rate. It will convert, but it will be giving you a linear convergence rate. So as an user, what you can do, and we will talk about that. First is we'll talk about how to pose the equations. I'll discuss some of the way that you must avoid posing the equation. Like the way the equations are written and derived, that's not you should code an equation in a software. It's completely different things. Coding is completely different than when you read an equation in a book or derive the equation. It's a new mathematically they are equivalent, but they are not numerically equivalent. So you have to be careful there. But anyway, we'll talk about those. Now, what it does is that generally what we do is something called now this alpha, the way these things are adjusted internally, and Aspen actually does not give you access to many of their solver settings. Like even those solvers which seems like give you access to a lot of those, like for example, I collaborated with Professor Bigler quite a bit, who has one of the developers of the IP-opt, right, which is used as a leading optimization solvers. And he tells, I have probably more than 1,000 parameters here. And it's only out of that maybe 50 parameters are exposed to the users. Others are set when he tried many systems and do that. So that is how it is. Aspen even actually exposes very few parameters, but internally a lot of things are going on. So one of the thing, and that is why I tell you that when it sits, it is doing something, and then fails. What it internally tries to do, one thing is that this alpha k, as I said, that this derivative that you are getting here, it's just a local approximation. So you are making step based on these, but you need to adjust the step length. So how do you adjust the step length? So Aspen generally do not have some of the other approaches that are there in many other solvers, but one of the standard approaches it follows is that what we call the backtracking line search. So what you do here is that you start with a sufficient large value of alpha, right, that we generally can start alpha equal to 1. So that's the step length. That is what you wanted to take. Then what you do is that you calculate this one, this guy, and then you are basically saying that if I am actually solving it, that basically meaning is that I want to keep this equation in front of your eyes, like f of xk equal to 0. So what does it mean is that whatever is the value that I am going, I want to go to a descent direction. So if I'm having a value of 1000 or 1000, I want to take it to 0. So what it really tries to find out is that what I have right now with the step versus what I am right now, is this new step leads to a sufficient decrease. If I had a value of 1000, is it going to like 800, 700? Because I want to take it to 0. If it is saying no 1000, but you are just 999, or it actually an ascent step, like 1001, 1002 or whatever. Instead of a descent, it found that when it took the step, it is an ascent step. You should not take that step. So what should you do? So it actually calculates that this is whether it's a sufficient decrease. If it is a sufficient decrease, then you said whatever is the value of alpha k you consider, let it be, and then you are done. Otherwise, you need to keep cutting alpha and keep repeating it. So that means that if this alpha becomes 0, you are stuck. So sometimes it will keep complaining, saying, oh, we are stuck at it is stuck at a minimum, but that it does not seem to be a solution. And that is basically what is happening, is that it cannot take the step, and when it keep cutting it, it finds a solution that where alpha k is close to 0. So it's stuck at a minima, or it is cannot find a solution. We are stuck at a point which is not the minima. So that is what is the problem that is coming. So how it basically what it is doing, it is backtracking. It comes with a very large value and then keep reducing it, reducing it. That's what it tries to do it. This is an associate computational expense. Now the question is, how do I determine the sufficient decrease here? I'm sorry, there is an O missing here. I will correct it. Sorry for that, I just saw that. For determining the sufficient decrease, you actually apply one of these conditions. So Arimijo or a Wolf or a strong Wolf or Goldstein conditions. You will really do not need to get into any of these because Aspen does not expose you to all of these, but internally it actually keeps checking. So when you see that it is complaining, the way you understand mathematically, at least you see that this is what it is trying to do, but it is calculating the derivative, it is trying to take a step, but it is not a sufficient decrease, and the moment it is trying to do this is it is actually coming to a zero solution. So what it basically means is that it can be related to a derivative calculations, like which is not really meaningful approximations at that point. The other issues that comes because of some of the equations become yield conditions. So both cases will lead to this thing. So another approach that is, to the best of my knowledge, AspenTech has not yet done this, but we have a trust region approach, which I will skip, but any of you are interested, we can discuss about this. It's pretty complicated, but we will skip that one. So concluding remarks is that types of process model depends on the unit operations, what mechanism we are considering and modeling and how we are doing. You must always remember accuracy versus computational expense and the difficulty of applying finite different schemes, that which we talked about that one before. And then finally what I will say is that you must do careful considerations of model formulation, initial guess, solver algorithm, and the parameters. So when I will go over the tutorial tomorrow, everything that we discussed here mathematically, I will try to cover a lot of those things tomorrow, and I'll show you what Aspen exposes, what those parameters mean, and what values you should be setting there. Okay, so with that I end here.